Welcome to the Astrophysics Podcast. When I was a little kid, maybe in 7th or 8th grade, we had a school assembly where a representative from NASA came in to talk with us about astronomy. I will never forget how he started his presentation. Just to set the scene, this was a gymnasium full of grade school students, kindergarten through 8th grade, all sitting on the gym floor with legs crisscrossed underneath us, looking up at this guy. He started out by saying, "Now, I know you've all heard that the Hubble telescope had a mirror that was out of alignment. I want to assure all of you that we sent a mission up there and fixed the mirror, so now we're getting great images out of it." My 8th grade self was just thinking, what on earth is this guy talking about? But it was true. Many of you listeners might not know this, possibly because you weren't even born yet, but the Hubble telescope was, when it was first launched, not everything had gone perfectly according to plan, and one of the mirrors had an aberration that they needed to send a manned mission up to repair. To me, this NASA representative trying to reassure a bunch of confused grade schoolers that they had successfully repaired the Hubble telescope really drove home how worried NASA must have been that the Hubble was becoming some kind of PR nightmare. Whenever you spend a lot of taxpayer money on a big project like Hubble, there's, of course, always going to be public pushback saying, why are we throwing our money out into space? And when the telescope doesn't even work the first time and you have to spend more money to send astronauts up there to repair it, well, you can imagine why NASA was so worried about their public image. Fortunately, any negative press that NASA might have gotten at the time has basically faded into obscurity. I vaguely remember one of Gary Larson's The Far Side comic strips making a joke about it, but that by itself tells you just how obscure this story was. No, once the public could finally see images taken by Hubble, any doubts that we might have had were completely washed away. By sending a telescope into space, we finally had this totally new way of looking out into the cosmos. It's hard to overstate just how much the Hubble telescope has improved our ability to understand the universe we live in. To give you some sense, it's now 30-year-old technology, and other, newer space telescopes are now out there, and yet still, astronomers around the world furiously compete for the opportunity to use Hubble for even brief windows of time. My dad once said to me, if they were ever to make a list of the 7 wonders of the modern world, the Hubble telescope would be on the top of that list. The idea that as a society, you expend considerable resources and effort to send a telescope into space just to be able to see what's out there. It said a lot about who we were as humans. We were curious about the universe around us and were willing to go to great lengths just to learn what's out there. But now, this generation has a new telescope, the James Webb Space Telescope, or JWST, as astronomers usually call it, mainly in order to reduce the word count on their grant proposals. To give you a sense of how big an upgrade James Webb is over Hubble, imagine any technology back in 1990 when Hubble was launched. Imagine computers in 1990. Imagine cameras in 1990. Think about how much these have improved just on consumer devices. Now imagine applying that big an upgrade to the Hubble telescope. The James Webb telescope is like getting new eyeballs implanted into your head that can see farther and deeper than you've ever been able to see. And already we're learning totally new concepts about the formation of the first galaxies in the universe by looking at the most distant galaxies we can see. My guest today is at the forefront of these discoveries. Her name is Dr. Erica Nelson, and she is a professor of astrophysics at the University of Colorado Boulder. Today, she is going to tell us more about the James Webb Space Telescope and what we can learn from it, including details about how the very first galaxies originally formed. I'm Paul Duffel, and this is the Astrophysics Podcast.
And follow-up question, what are your feelings on cursing?
Well, go for it if you want to.
I'll try to refrain.
That's something.
It really gets people's attention when you throw an F-bomb,
It does. I know. I could amp up my ratings.
Exactly.
All right, good. So far this has been going well. Let's
do the thing.
Let's get started.
Yeah.
So I guess I should do some kind of intro. So welcome to the Astrophysics Podcast. I'm Paul Duffel, and my guest today is Dr. Erica Nelson, professor of astrophysics at University of Colorado Boulder. Dr. Nelson, thank you for being on the program.
Delighted to be here, Paul.
Don't have to laugh so much when you say that. So I guess hopefully
It's off to a good start.
it's hopefully it's clear to our listeners, my parents basically, but our listeners that that Eric and I have known each other for a little while.
Correct. We have.
I first met you we were both at the CFA, Center for Astrophysics, Harvard-Smithsonian. That's right. And now you're a professor at Boulder, and I'm a professor here at Purdue. So I'd like to start things off by talking about you personally and how you got to be a scientist before we get to the actual science. So let's start by telling me a little bit about where you grew up.
I grew up in Minneapolis, Minnesota, which is a delightful place to grow up. I went to this really cool elementary school where they were basically, like, their whole philosophy of teaching is, all right, 6-year-old, do whatever you want. Which was cool, because then you get to structure your own day as a 6-year-old. And they're like...
Was that your whole school experience? Because that doesn't surprise me.
Yeah, correct.
that's
and here we are.
Tells me, that by itself tells me volumes right there.
Yes, it should. I don't believe in rules. Yeah, they told us, like, hey kids, why don't you do a report on a planet? And I was like, that's cool. Black holes are kind of like planets. I'm going to do a report on a black hole. And my teacher was like, really? That's what you're going to do? And I said, yes, I am. And then I did. And then I was like, well, I'm going to be an astrophysicist.
Oh my God, that's it?
That's
right
it.
There, right then and there?
Yeah, I was 7.
Well, that's like 3 of my questions that I was going to ask. Just completely shot down.
Shot down. Killed him. Killed him.
And what am I going to ask now? Do you have a memory of the first time you wanted to do science? Oh, hang on. That was already answered.
Well, I have a follow-up.
Okay.
So I was like, black holes, I was like, sold. And then I did a report on the Hubble Space Telescope. And I was like, when I learned about the fact that when you look really far away, you're looking back in time.
Yes.
I was like, this is the most mind-blowing thing I have ever thought about in my existence. I have to do this with my life.
Wow.
And so that's what I did for my PhD thesis.
It's just skipping a person.
Just skipping it.
Skipping
the problem years.
You're like, all right, let me start my PhD thesis now.
Yeah, and then there was like the years of like high school where I was like, you know what I should do? I should throw parties when my parents are out of town. And then I got in a lot of trouble, and then eventually I emerged on the other side. You know?
Okay, well that's nice.
Yeah.
So I mean, that seems so too perfect, right? You just like as you're a little kid, astrophysics, and then no deviation from that. You were just like, this is what I want to do, and then you got in trouble a bit as a teenager, and that, but then you stopped getting in trouble. Well, you got in trouble in various ways, I'm sure, but
yeah, but I had this high school physics teacher who was a real piece of work, and so I'd wanted to take a physics class like forever, and I was so excited to be in this class, and I'd always ask questions, and I was like just so excited about everything. And he had this sign in the front of the classroom that whenever you asked a question, he would just point to the sign, and it said, "Now is not the time." I am dead serious. He was like, his goal was to like kill curiosity of children. He was awful. But then I was like, and so he was like, just God. And so my mom went to parent-teacher conferences, and and she was like, what is my daughter doing something wrong? Like, she's just really excited about physics. And he's like, she's trying to humiliate me in front of the rest of the class.
Oh my God.
And my mom told me this. I was like, what? Like, dude has a PhD, an engineering PhD, and he's like, I'm embarrassing him in front of the class that he's taught for like 30 years, whatever. Anyways, I felt kind of bad, but then I was asking him a question after class because I was like, well, maybe if I just don't ask him during class, he will like hate me less or something.
Right.
And so I asked him a question after class, and he's like, I don't understand like why you are so like adamant about this. And I was like, well, I want to be an astrophysicist. Like, that's what I want to do with my life. And he's like, you can't do that. And I was like, why not? He's like, who's going to cook?
Seriously?
Yes, correct. In high school. And so that was whatever, 2000 something. Yeah.
Okay. So then you're like, okay, well, I guess I'll become a chef.
Exactly. Yeah. I was like, okay, I better get my chef skills on. And then I was like, well, since the only thing I want to eat is cookies, I'll learn how to bake cookies and nothing else. They're the only delicious food in the whole universe. Yeah, it was
Well, I should have baked cookies for you.
It's true.
Next time.
Yeah.
Wow. Okay. So that's that must have been pretty demoralizing. But did you? How did you take that? Did you take it like? Did it like, was it like a punch to the gut, or was it more like, screw you?
It was definitely like I definitely had like because I was told that in different ways by different people. Like I was told by my chemistry teacher, like, you don't want to be a scientist. Like, they're brilliant, but they just don't function like the rest of us, like in society. And like my track coach weirdly was like, no, you're not smart enough to do that. Like you'll be a politician. Like you're good at talking. And I was like, thank you for that. And this is when all your listeners judge me because I'm not good at talking. But yeah, it was weird. And so it just didn't feel like I had the right identity to do it. Like it was like I would always be just on the outside. I would never be one of the scientists, So it was weird. I just never felt like I fit in
That's
all
so
those
funny
math
to
and
me
science.
because to me your personality. Well, to me even though you do have a at times combative personality, but I think it fits in very well. There's a lot of people that are in science that are like that. Right? That you get excited and you want to know the thing and you keep asking the questions. Like that's exactly that's the kind of curious mind that does fit in here, I would think.
Yeah, it's just I think I don't know, and I think probably a lot of students in high school feel this way. Like they're just there's all these kids in high school, and it's they do they do math on Friday nights, and they are in math club, and they do a lot of Dungeons and Dragons, and there's they have their whole thing, and that's cool. And those were not my things.
Right.
I was more I want to spend all my time doing sports. I don't want to read books. I can barely even read. And so it was yeah, it just didn't feel like I was kind of it didn't feel like we had a lot in common, if you know what I mean. And so it just felt is this really is this where I'm supposed to be? I don't, so it was kind of a weird thing.
But you still had this idea. I mean, you had this idea in your head this whole time that this is what you want to do. You thought all this stuff about space and black holes and how looking into the past and understanding the universe. Still, that superseded all of that.
Yeah. I was just well, I was kind of okay, maybe I can just get through all the science stuff, and then I'll be able to do the stuff I'm good at, teaching or science communication or something. And then it wasn't until grad school that I was oh, actually, I love research. I love it. I love it so much. And I actually am kind of okay at it, which is nice. So that's good.
It's good to be kind of okay at it.
It's good to be kind of okay.
So that gets into then, so that when you started grad school, then I guess you felt a little more at home.
I wish I could say yes, but no, definitely not.
Still not. Do you at any point feel at home?
I mean, do you feel at home?
I don't know. I mean, not in any given room I'm in, but
I think maybe just no one ever feels fully at home or something.
Yeah,
I don't know.
Maybe that's true.
Maybe, yeah.
We're all a little restless.
We all feel like we're our own special snowflakes, I'm such a very special snowflake,
It could be. It's fair.
I mean, we're not. We're all just part of humanity, and that's beautiful and amazing. But it's just, I think I don't know. I think sometimes students, especially during their angsty years, are particularly troubled by the fact that the people around them aren't the same as them. You're I don't fit in with this. And I don't actually, I think everyone feels like that to a certain extent.
I guess that's true. At least at some point in your life, you'll always kind of feel
no one, I'm different. No one gets me, whatever. Yeah. I don't know. So I guess I just kind of think of I think of my students and just, that and especially high school students, that just because they don't necessarily feel that this is everyone around them gets them, it doesn't mean you're in the wrong place. You know what I mean?
Yeah. No, that's true. That's a good point. So I guess we were getting into like when you got into grad school
Yes.
and how when did you feel like you started like thinking like a scientist?
That's a good question. Definitely grad school. Once you start those kind of moments when your advisor gives you some kind of direction, and I had a fantastic PhD supervisor. I was like, Peter Van Dockum was amazing. But when, he suggests the direction to go, and then you think of follow-up questions yourself, and then you want to explore them. I feel like that is when I really started feeling like a scientist.
Yeah, that took me a number of years before I sort of started thinking that way, where I was like, oh, if you set up the problem this way, then you can figure this out, and just rather than being like, oh, I've been given this task and let me solve it,
check all these boxes. Yeah, when you are really kind of starting to set your own directions. I kind of think of it. Do you know the XKCD what ifs?
No, I don't.
Okay, they're great. It's like for example, what if you had a mole? Like the number mole
of
I know
moles.
This. Yes, of the furry animal. What would happen?
A mole of moles.
A mole of moles. Yeah. What would happen? And then you kind of get to go through all of the science of what would happen in that circumstance where you had a ball of fur, and so I feel like research is kind of that. It's just answering these what if questions. You pose a question to yourself, and then if it's an interesting question, then you answer it. And then you write a paper about it. It's cool.
It's pretty good.
Yeah, it's a great life.
Excellent. So now you're an astrophysicist. Mm-hmm. Goals achieved.
Goals achieved.
What are some of the things you like the most about your job?
I love that our entire job is that we get to be driven by our curiosity. Mm-hmm. The universe is just such an unbelievably weird and interesting place, and we just get to discover things about it and discover all the weirdness and then follow it and see where it leads. And I just cannot think of a cooler job than that.
Yeah. It's very, when you put it like that.
And we get to then teach students who also are curious about the universe. And they are, everyone is excited about the universe. There's no, I guess, especially like those listening to your podcast about space.
My parents.
Yes, your
parents. Hi,
Mom and Dad. Maybe my parents will listen too.
They could.
Yeah.
This is how I gain listeners. Is like.
I'll tell my parents about it, and then they'll tell their friends.
Exactly.
We'll have 10 listeners.
Yes. Before you know it.
Before you know it. But it's such an amazing, the fact that we live in an era where we are sufficiently able to produce food and shelter for ourselves, that we can actually expend resources to understand our origins and the universe is remarkable.
Yeah.
Truly remarkable. I am so glad I live now instead of in a time where I was dumping chamber pots on the street. It's really a better time.
It's pretty good. It's a pretty good deal. I know. I like to. I would always, especially when I was a postdoc, I would just be like, they just pay me to play around on my computer all day.
Yeah, totally. Yeah.
Now I have additional tasks, teaching and advising, which I find really fun.
Really fun.
But
yeah, it's just amazing sometimes what students come back to you with. They're these really junior scientists, and they come back to you with these amazing findings, and you just can't believe that they could already do that.
Yes.
It's just incredible.
Yeah, especially when they kind of lock in on that mode of becoming scientific thinkers and just being like, oh, but what if we did, then they get that. Yeah, then that's always, you're like, I've gotten them. I
lured them into the trap.
Yes. I love that. And is there anything you don't like about your job? I might edit this part out, depending on
What I answered.
Is there anything you don't like about your job?
Currently, it's more that something I don't like about me rather than my job. Like, I wish that I was faster at doing everything so that I didn't have to work so many hours.
Oh.
Yeah. I work a lot of hours.
Yeah.
I feel like just to get all the things done that I have to get done. And I feel like I'm still only getting like 20% of my job done. But it's just like, I like all the different components of the job. It's just they sum up to a lot more hours than are available to me. And so it would be great if I could just do everything way faster.
What do you think sinks a lot of that time away? Is it like meetings or?
I mean, I think, and it's like all the meetings in and of themselves are like good things, right? It's like more communication is always good.
Yeah.
But I think it's definitely, I feel like this is such a banal answer. Transitioning from one thing to another thing is like really hard. To like, if you're in meeting mode and then you have to transition for like half an hour to research mode and you're just like, it's like trying to get the plane to take off.
Yes.
But if you have a really short runway and you're like, come on, brain, you got this, or you're going to go crashing into the ocean. Like, let's do this, Yeah.
You've only got so long.
Oh,
so
yeah.
much. Yeah, I guess I get that too. It's very hard to do your own research once you're in professor mode because you have so many other things. It's hard to fill in the gaps with research.
And I do feel selfish wanting to do my own research and publish my own papers instead of just helping students with their papers. But it also is like what makes me want to do the job, kind of.
Right, that's
like,
what you were originally trained to do. That's the funny thing about becoming a professor.
No, it's weird.
Is you're hired based on your ability to do your own research, and then you're like, good, congratulations, you're now a manager.
Yes, you're now a manager of people, budgets, and students. Yeah, and you need to deal with all these things that you have no idea how to do. Yeah, you just kind of feel out of your depth.
Yeah.
I also wish I was a better manager of people. I've been reading books, but I'm not good at it. Like, I'm working on it.
Well,
but
we
like,
weren't trained on this sort of thing.
No, we were not.
They were just like, well, you'll naturally be good at it, I'm sure. You know physics, so you'll be good at it with people.
And like managing them. Yes.
Managing them.
Yeah, and you're like, interesting. I know. So I feel bad for like my early students because I just feel like I'm not a very good advisor yet, and I'm like working on it. But I'm like, I'm sorry, I'm not good at this.
Sorry, you're the test student.
I know. You're such a brilliant guinea pig, but like, like it sucks to be a guinea pig. Yeah, it's rough.
So, okay, what would you, I don't know, maybe this is kind of a repeat question, but what would you say motivates you the most in your professional life? In other words, gives you the energy to get, like, out of bed and work on these things? I guess you've already said, kind of. You get excited about the research itself.
Yeah, lately, and this has kind of been like a thing that has driven me for some time now, but I would say lately it has been the James Webb Space Telescope because it is just so mind-blowing what we can see with that telescope. And it's like anytime you look at the universe with new eyes, you just see all the stuff you weren't expecting to see, and it is remarkable. So I just get really excited about the discovery aspect these days.
All right.
To just look at these images and like, what is in these images, It's so cool. It's really cool. And I think I had before we met at Harvard, I had a very rough first postdoc, and such that I was starting to apply to jobs that were not astrophysics jobs because I just felt so discouraged. I felt like so horrible about my existence. And so it was really the fact of getting JWST data that is why I'm still here, because I was about to bail.
Wow.
I was like, this is horrible. I hate
That's crazy because I never got that sense from you when we were at the CFA at Harvard, but I'm not even I'm curious as to what your previous institution was, but I think that would be a little bit mean to say what it is. People can look it up if they want to. But to me, when I met you there, you seemed really motivated and excited every day to come to work. So at least maybe at the CFA, it wasn't that you would kind of.
I loved the CFA.
Yeah.
Everyone was so like supportive and nice, and I was so excited to be there.
It's a great environment.
It was a great environment, and it has definitely kind of driven my. I really think that environment is really important, and kind of the environment that we create every day for each other.
Yes.
And so it's really become something I work hard at. I'm not always good, right? You have days when you're cranky and you're just like,
yes.
And so like, obviously I'm not always good at this, but I do try really hard to make sure that like the thing I'm contributing to my surroundings is, kindness, and to like help that place be as good, like
That's
to do
funny.
what I can to not be a jerk,
For me, my bad days are when my brain just doesn't work and I'm spaced out. And so I give completely useless answers to any question someone has. It's actually, I have to do this I realize I have to do this podcast in the morning because like I can't. If I try to do it in the afternoon, it will be way more of a train wreck than it already is.
It's like a mushroom trying to interview a person.
That's right,
you're like,
exactly.
I have the brain capacity of a fungus right now.
Yeah, that's how I get that. And I feel really bad when I get that way because it's the same. It's a different thing, but I am creating an environment, right?
Yeah.
And when I get that way, I create an environment of like nothing you say matters. Because it's just going to go bounce off the fungus and
and into the dirt.
And
you're
dirt.
like, this is not helpful.
So I'm sad because you gave me a perfect transition when you started talking about the James Webb Space Telescope.
Oh yeah,
I know.
you just cut
like,
the rest of it.
Don't tell me how to edit my own show.
I'm sorry, Paul.
No, all that's gold. But I should say, because I was thinking of it, like what you said about environment is perfect, because the CFA, it's kind of the opposite of what you were saying before about that sign that said now is not the time, right?
Yes.
When you, right, pointing that sign, being like, we don't ask questions right now, like CFA was the, Harvard Center for Astrophysics, for those who don't immediately know what I'm saying when I say the phrase CFA really quickly. It's a perfect environment for exactly what you're talking about, of getting excited and asking just jumping in and asking the question, whether not worrying about whether it's the right moment.
Totally.
Because you can't pause and go like, wait, is this the right
Is this the right moment for the question?
Then you'll lose it. All its momentum will be gone. So anyway, I agree. I totally agree that environment is so crucial. I just wanted to link it back to that because I thought that was. So let me start by asking you this. When you meet a new grad student or a fellow scientist and they ask you what you work on, what do you tell them?
I tell them that I use our Just Wonderful Space Telescope, JWST, to look back to close to the beginning of time to understand how the first galaxies form.
Okay. And now you said this right off the top about this exciting concept of looking back in time, but why don't we dig into it a little bit in detail and explain what that means?
Yes. So, light travels really fast, but it actually does have a finite speed. And so if it has to travel a really long ways, like from billions of light years away, it takes billions of years to arrive to us. And so if you can look really far away with a really powerful telescope, then that means you can look to very early times when that light was emitted. So you're essentially looking back into the past, which is just a remarkable concept.
So like, for example, when we look at the sun, we're not seeing it as it is exactly now. We're seeing what it looked like 8 minutes ago, because light takes 8 minutes to come to us.
So if the sun were to, for some reason, spontaneously turn into a black hole, we would not know for 8 minutes. Consider that.
Well, So I guess we can carry on with the podcast for at least 8 minutes.
Correct.
So then if we look, so then extending that to very, very distant galaxies, so you say billions of light years away, we're seeing them as they were billions of years ago. And so what do we do with that information?
So if we can look far enough back, we can look back to the time when galaxies like our Milky Way were forming for the first time. It was, the universe started with the Big Bang 14 billion years ago, and then all of the structure in the universe had to form from that to where we are now. And so if we want to understand how that structure formed, there's a number of different ways we can do it, but I think definitely the coolest way is to look back and actually see the structure.
Just
in
look
the
at it directly, and just see. So if you're looking at more and more distant galaxies, each of them is a snapshot at a different time. And so you can actually see the evolution, or you're not seeing any one galaxy as it evolves, so it's not exactly like turning on a movie, but it's you can see the evolution of what galaxies looked like.
Totally.
At each point in the past.
Totally. It's like piecing together how humans grow it from a picture of a different person at every right. at each month of their life,
right.
So it's cool. Yeah. And so, it's different people that you're looking at, but you can kind of see that gradually humans get bigger and hairier as they age.
That's fair. So you learn general things about how galaxies evolve and how they grow. And so how do how do they evolve? They get bigger? They grow?
Yeah, they kind of, galaxy formation is interesting because it is kind of at the intersection of a lot of physical processes of very different scales. There's relevant scales down to the size of a black hole, and then there's relevant scales up to the size of the entire universe. And so it's really hard, the interplay between all of those different scales and the physical processes at all those different scales makes it a very complicated thing.
Because all of those different things are important that are going on. So what are these things?
So on the biggest scales, galaxies kind of form so we live in a cosmic web, this big spider web of universe. And so galaxies live at kind of the intersection of these different filaments, and gas kind of flows down these filaments into the galaxy that's at the center. And then that gas will condense until it gets dense enough and hot enough for nuclear fusion to ignite, and that is how the stars in the galaxy are formed, right?
Okay.
And then as those stars age, some of them become supernovae and blast gas back out of the galaxy, or that gas falls into supermassive black holes and that blasts gas back out of the galaxy. So you have these kind of galactic fountains of gas.
So the processes I've counted so far, you have, on the largest scales, you have gas flowing into the galaxies. You have the stars first forming and that affecting the galaxies, then the stars exploding and that affecting the structure of the galaxies. It blows the gas out of the galaxies, and then also gas falling onto black holes in the center of the galaxy, and that and then that creating all other outflows that also affect the structure. Is there anything I missed?
Yeah, you have the angular momentum of so all galaxies live in big kind of spheres of dark matter, which we call dark matter halos, and so those halos have angular momentum, and that drives the structural evolution of the galaxies. So there's another thing. First of all, first time bringing up dark matter, yes,
and
true.
Without much explanation, which is kind of how we don't have much explanation for it, other than it's most of the I guess mass in the universe that we can't really see, but that's what actually constitutes most of the, we call it the halo, but that's actually constituting most of the mass in the region. And so we don't see that directly. We're only indirectly looking at it from the galaxy, right?
Yeah, and it's, it's weird because there's this thing that we don't see. Our only evidence for it is its gravitational effect on the matter that we can see, on luminous matter. And so we weirdly kind of have to take it on faith that this exists, and it has there's a lot of predictions of this model that includes dark matter that are successful, but we haven't detected it.
We haven't seen it ever directly. It's always indirect. We see how it affected. There's many examples that are very close to direct, where you can see its influence very precisely, but you can't. But
we can't detect it.
We've never found a way of just looking at it directly, either in a particle accelerator, making it, or something like that.
Yeah, or figuring out any way to observe it in the universe. It's kind of wild, but we think, even though we haven't detected this, we think it kind of forms the scaffolding of our universe, of all the structure in our universe.
This is what you were describing before. You said the cosmic web, and I kind of let you just go with that. But what you said before is that when we look at the universe, we see these galaxies. But I guess what most of the mass of the universe is in this dark matter, and that forms this thing you called the cosmic web, which we call it that because of the way it's structured. It looks very web-like. These filaments going from one halo to the other.
Yeah.
But we never see that directly, do we? Or
there is gas, very hot gas in there also. So there are people that are working on trying to actually image the cosmic web in hot gas. So in principle, you could see the cosmic web if you could look at it in ionized gas.
If you can see the gas that's flowing, not the galaxies themselves, which are bright, but the gas that's flowing into them, it might be harder to detect directly.
Yeah, because it's very, very diffuse and very hot.
So what does your day-to-day research look like?
So currently, I am basically just using data from the James Webb Space Telescope. We're getting new data essentially every day from this thing, and it is just a box full of surprises. It's glorious. There's so much weird stuff in there. I'm kind of always looking for surprises and then trying to understand what they are and what their impact might be on our understanding of the universe. That's kind of
neat because that is also a link to you as a little kid being excited about the Hubble telescope. And now this is our generation's version of that.
It is.
So that's pretty cool.
It's amazing. It's so amazing. I mean, the stuff that we've found with that thing is just crazy. We thought it was going to be a telescope of galaxies, and it is that. It is also a telescope of baby quasars, which is very cool and very weird.
Baby quasars?
Baby quasars. Baby quasars.
All right, so we'll have to explain what a quasar is.
Yeah, so basically at the center of every single galaxy, at least massive galaxies, we think that there is this supermassive black hole that is lurking there. So a black hole with a mass of kind of 1 million to 1 billion times the mass of the sun. So big black holes.
Very, very massive.
Very massive. One of the things that has been challenging for us to understand is how those big black holes got there.
Right.
Because it's really hard to make a black hole that big.
Yeah, I would think.
It has to eat a lot of stuff.
It has to eat 1 million to 1 billion times the mass of the sun.
Yeah, in a finite amount of time. And there's kind of a, physical limit, we think, on how fast they can eat because, when they're weirdly, supermassive black holes, despite the fact that they're called black holes, are some of the most luminous objects in the universe. And so that radiation actually sets a limit on how fast they can eat. So it makes it it has been a long-standing theoretical challenge to figure out how we make these black holes big enough. And so we've been trying to figure this out for a while, and all of a sudden, now in the early universe, we're seeing all of the baby versions of these black holes. So we're actually able to, just like galaxies, see them in the process of growing, which has been remarkable and really helps us put constraints on our models, which is cool.
So the quasar, meaning that when the black hole is eating gas, it shines brightly, and we see it as what we call a quasar. And so then so when you call it, baby quasar is meaning, when you say baby quasar, what you mean it's a black hole that is shining brightly, but it's less massive. And so how massive are we talking?
So it doesn't sound that baby, if you're kind of not used to thinking about supermassive black holes. But we're talking about 100,000 times the mass of the sun.
Okay, but that's much smaller than any black hole that we've seen in that way, right?
At those times.
At those times, I see. Oh, right.
Yeah.
Okay.
Totally. And it's really this is a kind of region of massive black holes that we have a hard time studying because they're hard to detect. Yeah.
Right. So we understand. So for example, when we talk about black holes, there are the black holes that are seen by gravitational waves, which are 1 to 30 solar masses or something like that, and then there's sort of a gap where we don't know what goes on, I guess, and then and this is in that gap basically.
Yeah, exactly. And it's amazing because we have found so many of these black holes in this gap, and one of the weird things about them is there's kind of a relationship between the mass of a black hole and the mass of a galaxy now in the universe that is nearby to us. And all of these fall dramatically off the relation. They are really massive.
So you're saying, if we look at galaxies nearby, or by nearby meaning when you don't have to look way back in cosmic time, you're just looking at stuff now, you see a more massive galaxy, it'll have a more massive black hole in the center, and that's been established as a pretty remarkable fact of how galaxies must evolve with their black holes in some way. But then you're saying that when you look back at these baby quasars, you see that they're not fitting with that. They're not fitting into that relationship that we expected. That they're not. Are they more massive or less massive than you'd expect?
The ones we've seen so far, and this could be a bias in our observations, but the ones we've seen so far are very overmassive.
I see. So the galaxies are extremely young, and you would expect they would have a very much smaller black hole at their center. But they seem to be not. They seem to be already very massive.
Yeah, exactly. And so and so one possibility, if this ends up actually being correct, which more data needs to be taken.
Right.
If it ends up being correct, it could kind of suggest that instead of galaxies forming before black holes, the black holes formed before the galaxies, and they kind of provided the seed that formed the galaxy. So, which would be very, very cool.
That would be really cool.
Yeah.
So, was that idea out there in the zeitgeist before, or is it now just something we have in response to this data?
I didn't follow the black hole literature before, so I don't know.
Okay.
But it's definitely become a much more prominent possibility since we've gotten this data.
Right. That's very cool.
It's really cool.
Okay, so all right, what would you say was your most impactful contribution? What are you most proud of in your professional career?
So when the first JWST data came in, I was looking at it, so there's this image that President Biden released. It took him 2 hours, and so I'd already drinking too much champagne that I was just waiting for this image to be released. But we eventually got the image, and it was spectacular. And the thing I immediately noticed was there was all of these bright red objects in the James Webb image that were not in the Hubble image of the same galaxy cluster.
Bright red objects. So red galaxies? I guess you're going to answer this question in a second.
Yeah. But yes, they were galaxies.
Okay.
You looked ahead. Great job.
I didn't know the answer to this.
Yeah.
Most of the questions I ask, I already know the answer to,
Yeah.
but this one I didn't.
Well, and some are these baby quasars, it turns out. But yes, so we have these images, and so I found all these objects, and my friend and collaborator Rachel Bezanson and I started. We selected a bunch of these from the images, and we started fitting them with our best models of stars and gas and all the things that we think make up a galaxy to try to measure both the distances to these galaxies, i.e. their ages in the universe, and how much they weighed, because those are kind of the two fundamental parameters.
Right.
Very basic
Yes.
parameters. And so one of these things, so she ran these fits, and one of these things ended up having, being at really, 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 really early cosmic times, and already at that time was really, really, really massive. So massive at such early times that we immediately realized that it should not exist according to our models of cosmology.
I see.
And so we're on Slack all the time. It was early James Webb days, no one was sleeping. And so we Slacked our other colleagues, and one of our colleagues found more of them. And so we immediately wrote this thing up and submitted it to Nature like 2 days later. And it was really cool because the implications of this, so we're still trying to verify these, but the implications are profound if they're correct. It's because you really should not be able to make these in our standard model of cosmology.
You have these galaxies that are such an early time in the universe, and they're so massive. Like we had thought, okay, they build up mass, and you can sort of imagine charting how they grow with time, and if you extrapolate back, they'd be a certain mass. But these were much more massive, which meant somehow suddenly you just formed all this matter all at once together, and we just have no idea how you would just suddenly snap a galaxy into existence, a fully formed galaxy like that so quickly.
Exactly. Like one of the kind of key predictions of our model of cosmology, which underlies kind of everything we think we understand about the universe, is how it builds mass, how it builds the mass of objects. Gradually, it builds little things first, and then those little things crash into each other and make slightly bigger things, and then those things crash into each other and make slightly bigger things. And so you start building little things first, and then eventually you have big things. But to have really big things right away is just not how our model of cosmology predicts it's supposed to work.
Wow. So what does that leave us? Like what could be happening?
So the first thing is we need to actually verify that these things weigh as much as we think they weigh.
Right.
So I'm getting data in January to verify that.
Right.
If they are correct, if even one of them is correct,
right,
we have a problem.
Right.
Which is cool. I love problems. Eat that, theorists. So that's the first possibility, is that they're just wrong. We got their masses wrong.
Right.
But if that's right, then the next step, which some theoretical models have already proposed, is that you have to form the stars in these objects in a way that has never been predicted before, because you basically have to turn every atom of gas into a star. Normally, star formation is incredibly inefficient, right? It's less than 5% of the gas is turned into stars. So this is 100% of the gas is turned into stars, which is improbable, but also a less scary possibility than messing around with, the other knobs that you can turn, like dark matter and dark energy. So.
Right. So that would be sort of the most the most conservative assumption is that the data that the masses are off or something like that.
Our interpretation is just wrong. Yeah.
But then beyond that, then the most conservative, theoretical explanation would be that somehow you just really efficiently form stars.
Yeah.
That all the galaxies, just when it first starts out, it's particular, and they get sloppier as they get older. They don't worry about the details. It's like raising your second kid, But the very first one, you're being very careful. You're putting all the gas into stars, and being very careful in using it. So, but we still have no idea even how you would do that, even if that were true. And then and you alluded to, you could come up with more fancy ways of fancy theoretical knobs you could tune, changing if you changed things about how dark matter or dark energy behaved in the universe, you could is that because it would change our expectation for the age of the universe or something like that? Or
so there's ways, what we think dark matter is in principle is a very efficient at forming structure in the universe. It's very low energy, and so it's very easy for it to collapse in order and form kind of the foundation of galaxies, the structure on which these galaxies are built. But you could, in principle, make it even faster at forming structure if, for instance, you have part of the dark matter that is made out of baby black holes.
Oh, I see.
Yeah, our colleague, Julian Munoz from Harvard.
Oh, yes, yeah.
Yeah, is one of the people who's suggested that, actually.
Oh, okay.
Yeah, but so you can basically, if you have some part of that dark matter that is comprised of black holes, then it would be even stickier, and it would stick together and form the structure even faster than our current predictions. So that would be a way to solve the problem. And then, there's these kind of dark energy models that also change how the structure forms in the early universe. So it's basically you're trying to get ways for structure to form more quickly.
But increasingly fancy, complicated ways of changing what we think, overthrowing what we think about physics to make these galaxies exist. But I guess we're still at the moment in the stage where we're seeing if it's even true.
Yes.
And
I really love lobbing grenades at theorists, but I really, I want them to be. Even with that, I still want to lob the least destructive grenades first. So
right.
That's where we're at.
That's fair. That's very good. So that was very recent because JWST just I feel like just JWST just launched just yesterday, and we're already getting so much. We're just learning so much more about the universe and new things. So we're learning. That by itself, just seeing there's some red. It looks like there's some. What are those red spots on that image? And then that turning into what galaxies don't form the way we think they do.
Totally. It's wild.
It's very wild. That's very exciting. So I think you've made a good case for the James Webb Telescope already, and you've already said that it's not just galaxies. We're seeing all kinds of other stuff with it, like you said, baby quasars, and there's so I guess I'm going to ask a more broad question, and we'll see if you have an answer for this. In your opinion, why should we care about astrophysics?
I think that we as humans, part of our nature is that we want to understand our origins, and we want to understand the world around us. For thousands of years, people have been telling stories about space around us, and have been telling stories about how we got here. And so I think it's just part of our nature to want to know that, to want to be able to explain how we got here. And the way we answer those questions now is different, right? Because we can actually launch telescopes into space, which is amazing, instead of just saying oh, the Milky Way, that looks like some god spilled milk in the sky,
Yes.
But we can actually study those stars, study their ages, study their chemical abundances, and reconstruct the formation history of the galaxy that we live in. It's remarkable, but I think it's part of being human to want to understand that.
Mm-hmm. To understand this place that we live, the universe.
To understand our cosmic origins.
Yeah. Well, that's a good reason to care. I'll go with that. So what is next on the horizon for you? What are the next big questions to tackle?
I think that it's a little bit, this is a slightly strange time in my field of astrophysics, for the reason that I think there are some questions that are scientific method driven, where you have a question about physics and then you structure a hypothesis and then you answer it. Mm-hmm. I think, interestingly, at this point in extragalactic astrophysics, the most exciting new insights are going to come from just observing, trying to noticing new things, and then actually trying to understand what they're telling us about the universe.
Right.
So one of the things we found recently is that so one of our key kind of pieces of evidence for the existence of dark matter is that we have these rotation curves which are flat.
Okay,
so,
meaning that they're spinning at that things far out are spinning at the same velocity
as things interior, which means that there basically has to be a lot of extra mass that we can't see, which is strange. But one of the things we've found in some of our early James Webb data is that these rotation curves at earlier cosmic times actually fall, which means that there isn't dark matter in that portion of the galaxy. So
I guess the conclusion then is that dark matter at these early times seems to not be as extended out. The halo is not as extended out. Is that right? Or
we kind of think it might be the opposite. Like the like.
Good to see I was paying attention.
We think that like the luminous matter had to was much more effective at collapsing, and so it's very concentrated and it's dominating over the dark matter.
Oh, I see. So the dark matter it is extended, but it's negligible. It's a negligible contribution to the GATs in that sense. So
in the inner parts.
In the inner parts of the galaxies. Mm-hmm. So that tells you how much dark matter is around, I guess, or isn't, or lack thereof.
Mm-hmm. Yeah,
I see.
Which is interesting. Yeah, so it suggests that like the coupling that we see now between dark matter and normal matter is very different at early cosmic times.
Oh, well, that's very weird.
Yeah.
And we had no idea that would be the case.
There was some indication in observations a couple years ago that we were seeing indications of that, and now we're seeing a lot more evidence for it with James Webb. Yeah.
I see. But that's one example, just as you're saying.
One example of many.
As you're saying, because the original question is like, what's next? And the answer, like, it sounds like the answer is who knows, because it's really just look out there and try to find stuff.
Yeah.
Which is exactly what you're saying you did. That's what led you to this this discovery of these massive galaxies. It's not like I'm going to try to find massive galaxies. It's let's see what's there.
Yeah. What are these things? What are these bad boys? Yeah. Yeah. What are these chunky individuals? Yeah.
That's very cool. And so I guess right now, because I mean, the James Webb Telescope will be just taking more and more data, and I guess it's just more to look at, and who knows what else there'll be.
Mm-hmm. It's wild. It's wild and woolly out there.
That's great. I have no idea how to end this now.
Perfect.
All right. Well, that's amazing. And it sounds like there's just so much more to come. So thank you so much to Dr. Nelson. I had a lot of fun talking science with you, and I hope you'll join us again sometime.
Thank you very much for having me.
Well, that was fun. I always have a great time talking with Professor Nelson, and I'm so glad she could sit down with me. And I'm also so glad we got to hear about some of the great results coming out of the Webb telescope. I had no idea about those baby quasars. So thank you so much, Dr. Nelson, and thank you to our listeners. We will see you next time. The Astrophysics Podcast is supported in part by the National Science Foundation under grant number AAG 2206299. All the music that you hear on the Astrophysics Podcast was written and recorded by Britton Ashford from her album Trotter. All songs are used with permission from the artist and producer. The music sounds even better with lyrics, so look her up if you enjoyed it. This podcast is produced in beautiful Lafayette, Indiana by me, Paul Duffel, professor of physics and astronomy at Purdue University.